Another example of being able to find max, min, and saddle points, this time for a transcendental function, e to the 4y minus x squared minus y squared. We're going to start by finding the partials. Both of them are going to use the chain rule. So for fx, right, that's going to be equal to, obviously, e to the 4y minus x squared minus y squared. However, we just multiply by the derivative with respect to x of what's in the numerator. That's going to be a negative 2x. Now we need fy, and that's going to be the same thing, e to the 4y minus x squared minus y squared, and then we're going to multiply by the derivative 4 minus 2y with the derivative of what's in that composed function. So 4 minus 2y. Right. And remember what we have to do is we have to set these both equal to 0. Now this looks pretty horrific to solve, but one thing to remember is that the function, the natural logarithmic function e, will never reach 0. All right? It becomes asymptotic as it tends towards 0. So this will never equal 0. This will never equal 0. And so that really means that all we have to worry about is negative 2x equals 0, which implies that x is 0. And then we also have fy, which is going to be 4 minus 2y. And I think we can clearly see that y is going to be equal to 2 for that. All right, so we're going to have 4 minus 2y equals 0, which implies that y is equal to 2. So we only have one critical point, 0, 2. And so, of course, what is the classification of that point? Is it a max, is it a min, or is it a saddle? So that means we have to solve for d. And to solve for d, unfortunately, what you're probably going to notice is that we're going to have to use a product rule to find both fxx and fyy. All right, so it's not going to be easy, but we're going to do what we can. So for fxx, the derivative of negative 2x is negative 2, and then we still have that e to the 4y minus x squared minus y squared. And then plus, so we have negative 2x. We still have another e to the 4y minus x squared minus y squared. And then right here, we still have to multiply by a chain rule, another derivative with respect to x. That's going to be another negative 2x. Right? So if we wanted to, right, that's going to give us a 4x squared. Then we could just factor out a 2 and then e for all of that. So if I factor out the 2e to the 4y minus x squared minus y squared, that's going to leave us with negative 1 plus 2x squared. All right, so that's just for fxx. All right, now we still have to take care of fyy. And fyy is another product rule. All right, so, but very similar to the previous, we're just going to have basically a duplicate of this term, except it's going to be squared. So the derivative of this 4 minus 2y with respect to y is negative 2. So we have a negative 2e to the 4y minus x squared minus y squared. And then plus, when we take the derivative of this e, it just stays e. But then we take the derivative up top here, and that's going to give us a 4 minus 2y times the other 4 minus 2y. So we're going to get 4 minus 2y squared of the e 4y minus x squared minus y squared. All right. Mercifully, fxy is not too bad because there's no product rule. All right, so fxy, we take the derivative with respect to y, and that's going to be negative 2x. We still have that pesky e to the 4y minus x squared minus y squared. Fortunately, though, we just multiply by the derivative with respect to y, and that's going to be a 4 minus 2y. All right. Now, let's look at the function d, and then we'll consider that we'll make it a lot easier for us. So d, now remember, d is equal to fxx, fyy, minus fxy squared. All right, so I'm going to write it out really long first, and then we're going to make it really easy for us. All right, so that's going to be equal to, now remember we had this expression, the 2e to the 4y, so 2e to the 4y minus x squared minus y squared, and then we had 1, or negative 1 plus 2x squared. We're going to multiply that by fyy, which we found to be this, we should have factored out that e. So if we factor out the e from here, or this e term, I just didn't do it in that previous step, that's going to be just an e to the 4y minus x squared minus y squared. And that's going to leave negative 2 plus 4 minus 2y squared. All right. So that's a times. And then finally, we have to subtract out fy squared, or fxy squared. So that's going to be negative 2x, 4 minus 2y quantity square. And then we have all of that e squared. So that's e squared, or e2 times 4y minus x squared minus y squared. All right, now, this looks pretty horrific. All right, but let's think about what we're really trying to do. Do we need the actual value of d, or do we need the sign of d? And do we need the sign of fxx? And we need the sign of fyy? Well, of course, we only need the signs. Okay, so since we only need the sign of d, then we can ignore any factor of e to the 4y minus x squared minus y squared, because we know that that number is always going to be greater than 0. All right. And so if we really wanted to, we just get rid of this, we get rid of this, and we get rid of this. All right, I'm going to call it not d prime, but I'm going to call it d sub 1. It's really not d, but it helps us a lot. So I'm going to call it d sub 1. It's going to be equal to negative 1 plus 2x squared. And then we also have, we're going to multiply that by negative 2 plus 4 minus 2y quantity square. And from that, we're going to subtract out that negative 2x, 4 minus 2y square. All right. And just want to make sure we did all that okay. I think we might have forgotten to square this 2x because everything's squared. So let me make sure. So we go back up here. We're taking the partial. So yeah, we'd have to square that 4x. All right, so this 2x to make it 4x squared. So this should be right here. That should be a 4x squared. All right, so and then when we go down here, do this again. So sorry about that, algebra error. All right, so now that we have d, now thankfully, we only have one value to worry about, and that value is 0, 2. So let's find d at 0, 2. I'm going to call it d1, and it'd be really nice if it was less than 0, so then we wouldn't have to plug into the second derivative. So that's going to be negative 1, because that 2x goes to 0, negative 2, so that's nice because when you substitute 2 back in here, that's 4 minus 4, which that's 0. And then this whole thing, if I substitute a 0 in for x, that goes to 0. So that's 2, which is greater than 0. And so remember, if for some reason your d is bigger than 0, then you have to go back and you have to remember what happens with fxx. All right, now, when we substitute back in for fxx, all right, and fxx is way back here, all right, notice that if we substitute back in this value, and again, we don't care about this because this is always bigger than 0. So if we substitute back in for negative 1 plus 2x squared, so I'm going to call it fxx1, all right, just because it's not really fxx, all right, that's going to be negative 1 plus 2 times 0 squared, which is negative 1, which is less than 0. So finally, what that means is that we have a max at the point 0, 2. And of course, the maximum occurs at when f is 0, 2. So that's, remember our original function was e to the 4 times y minus x squared minus y squared. So that equals e to the 4th power. Right? That's the exact value, hopefully. Otherwise, we've wasted about 12 minutes of finding the maximum of that function. And so finally, we have a max at the point 0, 2, e to the 4th. Hopefully, maybe, potentially, feasibly. Of course, we always go back to the graph. All right, so let's go back to the graph and see what happens with this. So I'm going to insert graph into here. And for those of you that graph this first using your Desmos, all right, this is what it looks like. That's not all that helpful because, I mean, it kind of shows that it's going up, but that doesn't mean somewhere up here it's going to do like a dip and a turn. It's going to turn back around. So I did zoom in and prepared a second graph. And this one has this shape. All right, now, the good news is with this one, the value is really close to C, that is a max, so that's good, and it's somewhere between 50 and 60. If I was to approximate, I could say something like maybe 54, 55, something like that. So max somewhere between 50 and 60. But remember, we knew it was e to the 4th. Now I'm going to stick e to the 4th in my calculator. And this is where the magic happens, hopefully. I don't know what e to the 4th is. Whew, that's a good thing. 54.598. All right. So about 55, which makes total sense from this graph. All right, so I do urge you once again, once you get your maximum minimums and saddles, use the Desmos program to verify your solutions. All right, so that was a pretty cool problem because we wouldn't be able to figure this out. For most of us don't know that 54.598 is e to the 4th. Of course, we could just go through and use that trick where you just keep zooming in on your calculator, or you could just use like a max or something like that if you have a 3D grapher. And eventually you'd get there. But this finds the precise value. And that's the beauty of calculus. It gives us these precise analytic values that we can't get just by using technology all the time. All right, so we have one more example of these, and then we can move on to the other types of problems where we can try to use maximum and minimums.